we defined electric potential difference for a source between 2 points in space, A and B, as the minus the integral of the electric field of that source dot ds. And because this is a path-independent quantity, it doesn't matter what path we take from A to B, this potential difference will always be well-defined. Now, again, we have units here, and we call this, the unit is a volt. We denote that by a V. And over here, we see that that's equal to newtons per coulomb in SI units times distance, meters. So a Newton meter per coulomb. But recall that a Newton meter is a joule. So another way to think of that is a joule per coulomb. But remember, this quantity was defined in terms of work done on a test charge per test charge, so the units of joule per coulomb is not a surprise. Now, there's a lot of things that's very unusual about this. For one, why is there a minus sign? So let's look at it this way, that we defined, and I'll write this now as delta V from A to B. We defined it as minus the work on a test charge in going from A to B. This was on a test charge, divided by the test charge. Now, I'll just remove that. That might make it look a little confusing. And so we recall that the change in potential energy, UAB, is defined to be minus the work done in going from A to B by a force. Notice how this notation can be very confusing. We have a V for potential, and this should here be just a U. And that can often be confusing. So what we see is the relationship of these quantities. And another way to think about this is that the potential difference between points A and B in moving a test charge, Q2, from A to B, is the change in potential energy in going from A to B divided by the test charge. So just like electric field is the force per test charge, the potential difference is the change in potential energy per test charge. Now, why is that useful? Well, we can turn this around and ask the following question. If we move a charge Q, and sometimes we can say across a potential difference, delta V, then, so now instead of thinking about this test charge, if we have a potential difference between 2 points in space and we move a charge Q across that, then we know the change in potential energy is just Q times the potential difference delta V. And this idea is, again, the analogous before. If we put a charge in an electric field, the force is QE. If we move a charge across a potential difference, charge across a battery of a certain potential difference, then we know how much potential energy it is. Now, this is useful because now we have the idea that our energy principle tells us that the total work done by an external force will cause the kinetic energy of our chart of an object to change plus the potential energy to change. And now, if we're talking about potential energy coming from electrostatics interaction, we now can sum up the energy principle by saying external work causes delta K plus Q delta V. And this is something that becomes a major calculation tool that we'll look at some examples for. Let's consider a charge that's fixed at a point in space. We'll call that charge Q1. Non-electric forces are fixing this charge. And now let's consider a second charge, Q2, And we'll make both of these charges positive, so the product, or negative, both, so that the product of their charges are positive. And so we know that there's an interaction between these charges, and we've used a notation where we've said F12 represents the force on particle 2 due to the interaction between particle 1 and 2. And now what we'd like to consider is, remember, we'll fix this particle here. And now we'll move this particle along a path in space from a point A to a point B. And what we'd like to consider is the work done by the interactive force on particle 2 in moving from A to B. Now, work done on particle 2 is the integral over the path of the force on 2 due to the interaction between 1 and 2 due to this dotted into the displacement of the particle. And remember, that displacement is tangent to the path. And now what we'd like to do is to calculate this integral. Now, in principle, it can be difficult, but because we know the force law between these particles, and this is the key step, we know that this force is k q1, q2 over the distance r12 squared, and there's a unit vector, r12. This is unit vector at particle 2 pointing from 1 to 2. And because we know this, Coulomb's law, that will make this calculation easy. Now, in order to do it, let's choose a coordinate system. So we'll start again over here, q1. This will be at the origin of our coordinate system. And we'll place particle 2, q2, over here. And what we want to do is we want to blow up this path. So let's look at, I'll just dot in the path here. And we have our two key vectors. We have ds, and going radially outward, the force. Now, because we put particle 1 at the origin, it's now at the center, a central force problem, and that always tells us to use polar coordinates. And our polar coordinate system has a radial vector r hat, and we'll just take our theta hat in that direction. Now, what's the key idea to realize is that because work is how much force is in the direction of motion, then our force is radial, so all we really care about is how much of this displacement is in the radial direction. So let's look at that displacement vector, and we'll write all these out in vectors. We have a tangential part of the displacement and a radial part of the displacement. And what we can say here is this radial part is dr. Now, if we wanted to, and we had an angle d theta, and we were out at a distance r, then this arc length up here is r d theta. And this type of geometry for the displacement, breaking down that line element into the two pieces, is the key to this calculation. And so what I can do is write that vector ds, and I'll write it over here, as a radial part, dr r hat, that's the piece going radially outward, and a tangential part, and you'll see the tangential part will not be crucial. Now, in this coordinate system, the force is radial, so we'll write that as now k1, q2. We're a distance r from the origin, so there's r squared, r hat. Now, this r hat is very specifically the radial unit vector, whereas this was a more abstract vector talking about the interaction. So the next step is simply to calculate the dot product. So f dot ds, integral. Now, what are our paths? We haven't yet, let's just mark A here, and mark B out there. And A is a distance RA from the origin, and B is a distance RB from the origin. So what we're doing is we're taking our variable r from RA to RB, and that defines the path. Now here's the key step. When I take this dot product, r hat dot r hat is 1. Keep in mind, r hat dot r hat is 1, and r hat dot theta hat is 0. And so, as I said before, the tangential part doesn't matter. Only this radial displacement comes in. And this dot product, now here, if I really wrote this whole thing out, and I'll do it okay, and now when I take that dot product out, I get from RA to RB k q1 q2 dr over r squared. Now this is an integral that is a straightforward integral. It's just minus 1 over r, so I get k minus q1 q2 1 over r evaluated from RA to RB, and we get minus k q1 q2 1 over RB minus 1 over RA.
Okay, so you've just finished working on this problem, and you've worked out the work done by the electric field on this charge Q1 as it moves from this point A to this point B. And if you've done it correctly, you've got a negative answer. And I want to talk through with you why that negative answer makes sense. What do we mean by negative work? So you've just worked out the work done by the electric field, and you've gotten a negative answer. What does that mean? Well, let's think about this. I have some large fixed positive charge QS sitting here, and I took this negative charge Q1, I took it from the point A to the point B along this path, and the fact that this is a negative charge means that there's an attractive force pulling on this charge, pulling on this negative charge towards in the direction of the positive charge. So now let's imagine that I am pushing this charge from A to B at constant speed. Okay? So I'm the external agency. I'm holding this charge, and I have to push it because there's an attractive force pulling the charge towards QS. I'm pushing it outwards. So me, the external agent, I'm doing positive work. I'm pushing, 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 pushing to keep this thing moving at constant speed from A to B. When that is the case, when I, as an external agent, if I want to move this charge at constant speed along this curve, I have to do work pushing it against the field. What we say in that case is that, well, I'm doing positive work, but the field is pushing against me. So the field is doing negative work. If I'm doing positive work, then our sign convention is such that the electric field is doing negative work. So when you did the calculation, the result you should have obtained is that the work done by the electric field W should have turned out to be minus K, that's a positive number, times QS Q1. QS Q1 is negative, so this is negative, and there's a minus sign there. This is negative because QS is positive, Q1 is negative. And then when you did the integral, what you should have obtained is 1 over RB minus 1 over RA, where RB is the radius at which the point B is located, radius in the sense of distance from the source, and RA is the distance from point A to the source. You start at A, you end at B, and the result goes like 1 over RB minus 1 over RA. And since RB is bigger than RA, that means that this is negative. So when you did the calculation, you should have gotten 3 minus signs. A minus sign here, a minus sign here, a minus sign there, which is a negative answer. And why does that minus sign make sense? Why does the overall minus sign make sense? It's because the external agent, me, I was doing positive work to push the charge against the electric force. And that means that the electric field was doing negative work. Now let's change now the charge here. Let me use my eraser, and I'm going to put a positive charge here, Q1, instead. Okay, and we'll see what changes. So here is now a Q1 that this time is positive. So that means that over here, This sign stays the same, this sign stays the same, but now this is positive. So now, whereas previously W was negative, now W is positive. What does that mean? Well, now I have a positive charge here, positive charge there. The electric force is pushing the positive charge away. So if now I'm the external agent, I'm holding this charge, I'm moving it at constant speed along this yellow trajectory, I'm having to hold it back. The electric field is pushing on me. The electric field is doing work on me. The electric field is doing work on me. That means that now in this case, the electric field is doing positive work. I'm doing negative work. So in this case, W turns out positive. W is the work done by the field. In this case, it's positive. Now, to fully understand this, let's get rid of the external agent. Okay? Let's pretend there's no Krishna holding the charge and making it move at constant speed, and let's think about what happens. So let's keep this charge positive for a second, and let's suppose there's sort of there's some kind of a pathway, maybe rails of some sort, that will guide the charge from here to here under the influence of the electric force. And let's say we start with the charge here at A, and this force is pushing it in the outward direction, so it's going to accelerate because it's being pushed in this direction from A to B. No Krishna holding it now at constant speed, it's going to accelerate. And now you see that this makes sense because the electric field is doing positive work. That means that the particle is gaining kinetic energy. If it started here at rest, this F dot ds, oh, and I should, by the way, when I flipped the sign of the charge, I should have flipped the sign of the force. So once the charge is positive, the force is pushing this way. So now F dot ds is positive. I'm getting a positive answer to my calculation. Previously, when F was this way, F dot ds was negative. I got a negative answer to my calculation. So when the work is positive, that means that if I start with a charged particle at rest and there's no external agency controlling its speed, I just see what happens. It's going to accelerate. It will gain kinetic energy. So the electric field is doing work. The particle is gaining kinetic energy. Now, but suppose that I start the particle here at B and shoot it in this way with some initial large velocity. Well, the electric field now is going to be slowing it down. It starts at high velocity. It's decelerating. It's slowing down. And that corresponds to the electric field doing negative work. Or if I imagine flipping back to a negative charge, if I have a negative charge here, if I make the charge negative, suppose I start a negative charge here going rapidly this way. Then the electric force is going to slow it down. That's the electric field, again, doing negative work. So when the electric field does negative work, a freely moving particle is losing kinetic energy. When the electric field is doing positive work, a freely moving particle is gaining kinetic energy. And that's the other way of thinking about the sign of W.
We would now like to calculate the electric potential difference between 2 points in space for a simple point charge, QS. Now here, this charge could be positive or negative. And I'm going to consider a path that goes from A to B, 2 points in space. And I'd like to consider some arbitrary point on that where our electric field, here I'm imagining that the electric field is positive, and I have a little ds. And our definition for potential difference between these 2 points is equal to minus the integral of from A to B of the electric field of this source dotted into ds. Now, once again, we want a good coordinate system that will match this problem. We'll imagine our origin. So we're going to choose an origin where the source is, and our unit vector will point radially outward. So we'll have an r hat and a theta hat. And here, this is RA, and this is RB, and that's R. So now, in this coordinate system, we know that the electric field of a point charge is just QS over R squared R hat, and the displacement ds in this coordinate system, well, we've talked about this before when we had work, but we'll just imagine again that if you displace a little bit this way and then a little bit that way, where you have some angle d theta, and over there is dr, then our displacement vector can be thought of as a radially outward part and a tangential part. But the tangential part won't make any difference because the dot product of r and theta hat is 0. And so once again, only the radial part matters. And what we get here is the integral VB minus VA is the integral as our variable r goes from RA to RB. This dot product is KQS r squared dr. And now this integral dr over r squared is minus 1 over r, so there's two minus signs. So they come out, and we get KQS 1 over RB minus 1 over RA. And that is the potential difference in space between these 2 points for the point charge. But this result is the starting point for what we'd like to do to define a potential function. Now, let's imagine that instead of going to 2 arbitrary points, we started at RA equals infinity. And we have a charge QS that's at the origin. And we're taking a path that goes from infinity to a distance r away from QS. So that's our path. So here we have RB equals r. Well, we've done the calculation. We don't have to do it again. And so we see that our result is that the potential difference, V of r minus V of infinity, well, is equal to KQS 1 over r minus 1 over infinity. And 1 over infinity is 0. 1 over r minus 1 over infinity. And so we get that V of r minus V of infinity is equal to KQS over r. Now, this is a very important function. What does this quantity KQS over r actually mean? And in words, remember, this is negative of the work done in taking a test charge from infinity to a distance r away divided by the test charge. And so we can say that this quantity is the minus of the electrical work if we started a test charge at infinity and brought it to a distance r away from our original source. Minus that work divided by the test charge. We also could have said it was equal to the change in potential energy divided by the test charge. If we started with a test charge at infinity and we had our source here and we moved our test charge so that it's a distance r away from the source in our final state, and we calculated the change in potential energy divided by Q test, that's exactly what that quantity is.